Hello everybody and welcome back. We're still looking at the 2009 Grade 8 Gauss contest and we're up to question number 24. Starting at point P, Brina constructs a straight-sided spiral so that all angles are 90 degrees. Okay. And after starting with a line segment of length 1, each side is 1 longer than the previous side. So here's a segment of length 1, then 2, then 3, then 4. We're going north again at 5. We're going east again at 6. Next one will be 7, and that'll come down here to some distance, then 8. Okay, so we've got our spiral here, and we're spiraling out clockwise, actually. After completing the side with length 21, okay, so it might be a good idea to figure out, was that one that's going down? Is it going up, side? Is it going to the east or is it going to the west? That would be a good thing to probably know. So after completing the side with length 21, Brina's distance from her original starting point P will be between, okay, so we got a bunch of possibilities. 13 and 14, 14 and 15. Okay, so I'm guessing that I might need to use the calculator, and if I got something like 17.62 something, then my answer would be E. Okay. So as I said, it's probably a good idea to figure out what sort of, where length 21 is. We reproduce the spiral. 21 isn't that large of a number that you couldn't draw this out if you needed to. It's not going to be the most helpful thing, and it will waste a little bit of your time, but if you need to, that's fine. I'm going to draw a little bit, so here's our point P. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm pretty close there, but I'm actually not going to finish it off. And are there any patterns we notice, especially in the side lengths? Well, yeah, actually there are. If I'm looking at a side length that's going, say, south, going downwards, the next one that's going downwards is 4 more. And why is that? Well, because we go through the 3 other directions before we get back to going south. Okay? And then, 11 is 7 plus 4. 1 to 5, you add 4. 2 to 6 to 10, you add 4. So, okay, 21 is 20 plus 1. 20 is a multiple of 4, so 21 is 1 plus 4 plus 4 plus 4. So 21 is one of these ones that's going to go up. So, okay, that's a nice connection to make. All right, so Brina stops here. Maybe we call it point B. I don't know. Is there anything else we can tell? How can we figure out the distance from P to B? Well, one option we could have is to maybe start with calling this 0, 0, and then saying, well, what coordinates do we have? If we go up 1, so we'll be at 0, 1. If we go over by 2, it'll be 2, 1. Down by 3, it'll be 2, negative 2. Over by 4, it'll be negative 2, negative 2. Up by 5, negative 2, 3. And so on. So we could fill a few of those out and ask ourselves, is there any sort of pattern we're noticing in those? And we'd pay particular attention to the ones that head up to 21. So doing it with coordinates is one way. Another thing we could do is just say, well, what exactly happens when I go from the point that ends in 1 to the point that ends in 5? And what happens when what's the overall change when I go from the point that ends in 5 to the point that ends in 9? This avoids the coordinate system, but might yield roughly the same answer. So let's look if I'm at this point, this 1 here. Let's ignore P for a moment, but we're at the end point of 1. What's the overall horizontal change, the east and west change that happens by the time we get to 5? Because you'll notice we only go east once and then west again later. And the overall net change there is, well, 2 distances one way, but then 4 distances the other way. 4 units the other way. And up here, we'd go 6 one way and back 8 the other way. Now, we're always going to have a net change of 2 to the left. Always going to be 2 to the left. Why? Because you'll go some number n this way, and then you'll go down n plus 1, but then you'll go over by n plus 2, completely negating this n part and just going over by 2. And with the exact same reason, you'll also always go up by 2. Why? Well, from this point here, you go south by 3, and then 2 moves later, or 2 sort of lengths later, you go up by 3 plus 2. Or you go down by 7 and up by 7 plus 2, because it's 2 moves later. Okay? So the 3 cancels out with the 3, and you're just left with the plus 2 part. The 7 cancels out with 7, and you're just left with the plus 2 part of 7 plus 2, which is 9. Okay, so we always go over to the left by 2 and up by 2. Over by 2, up by 2. Over by 2, up by 2. And of course, this can be seen if you were to follow through with the coordinates as well. Okay, you'd get negative 4 and 5 next, and then you'd get negative 6, 7. Okay, so what coordinates would we have for 21, or what's the overall change? Well, we go from 1 to 5 to 9 to 13 to 17 to 21. So that's 1 2, 2 2s, 3 2s, 4 2s, 5 2s. So we go over by 10, and we'll go up by 10 as well. Okay, so, and that's from this starting point of 1. So our coordinates would be negative 10, 11 if we needed them. Okay? So now that I've got sort of my point P, 0, 0, and my end point B, negative 10, 11, I could use a distance formula. Okay? Now I could either use a distance formula if I know the distance formula between coordinates, or if I just quickly draw my spiral a little bit more. Measuring things in terms of sort of net change as we move around. I know this isn't enough spirals, but imagine it is. So my net change from point P to point B is I go over by 10. Now I went up by 10 from this point after the 1, but that's still 1 unit higher, so we'll actually have gone up by 11 from point P. We go up by 10 from the end point of the segment with the 1, but that was already 1 unit higher than P. So it's 10 and 11, and so if I just were to draw a nice little right angle triangle, because all angles here are right angles, then we just need to calculate the hypotenuse of this particular triangle. So we do 10 squared plus 11 squared, and square root that by the Pythagorean theorem. And this is also how the distance formula works as well. If you're going to use the coordinates that we had from the previous page, and you know the distance formula, it's the difference in the x-coordinates squared plus the difference in the y-coordinates squared. But you'll see this is the same thing as 10 squared plus 11 squared, and then square rooted. So either way we do this with coordinates or just spatial reasoning, we're off to the races. We have one more calculation to make. So we get out our calculators, or maybe we can guesstimate things in our heads if we didn't bring a calculator. I'll see what I can do. So this would be 221. Now I'm going to avoid my calculator. I will use it at the end in a moment. But I just asked myself, okay, square root of 221 is what whole numbers is that between? So I might ask myself, well, 221, what perfect squares is that between? Now this relies on my knowledge of perfect squares. So some perfect... Oh, what happened there? Some perfect squares that you might know, 169 is 13 squared, 196 is 14 squared, 225, 15 squared, 256 is 16 squared. Where does 221 fit amongst these? It's right between these two. So 14 squared is less than 221, less than 15 squared. So I don't really need to know exactly what 221 is in terms of its decimals. Just square root all the sides of this inequality, And I can see that the distance I want is between 14 and 15. And that's going to be an answer of B. Now we can, if you're worried, just confirm with our calculator, or this likely would have been a lot faster on our calculator. But we do the square root of 221, and that's 14.866. Okay, so yeah, it's exactly where we needed it to be, between 14 and 15. And that's a nice little trick. If you forget your calculators, I forgot my calculator once, and it was not the most disastrous contest I ever had. Okay, but there we go. And that finishes up question number 24. We have but one more question to go, question 25. So I will see you for question 25 in the next video. Thanks so much for watching.